So for circular motion, so far we've talked about angular velocity and rotation angle. Today we're going to take a look at how that affects the changing of the velocity, or specifically in this case what is called the things that make circular motion happen. And the first thing is centripetal acceleration. So centripetal has its own definition. We're going to write that down here as well. But centripetal acceleration is the acceleration of an object moving in a uniform circular motion. And then, of course, the next definition we're going to write down as well is the next sentence. Centripetal means toward the center or center seeking. It's kind of important when it comes to this because knowing that centripetal alone means towards the center seeking kind of is going to help guide you that everything that says centripetal in the future is talking about something that is center seeking or towards the center. So centripetal force, when we look at that later, will also have a force that is pointing in that same direction. So here we have this picture. Go ahead and draw this picture. So this is very similar to what we see before. We see that delta theta in the middle. We see delta S. We see R. Those all had to do with rotation angle, right? Because the rotation angle is equal to the arc length over the radius. We knew that already. And now we have velocity happening in two different spots, B and C. And now remember that when we talked about acceleration before, acceleration is a change in velocity, and that means that no matter what is changing with the velocity, because velocity is a vector, it has both magnitude and direction. So if the magnitude is changing, there's acceleration. If the direction is changing, there's acceleration. If there's both changing, there's acceleration. So in this case, the velocity might have the same velocity, right? It might be rotating with the same linear velocity, but it has a or say tangential velocity. It instead now, or it still has that, but it has also an acceleration occurring. And even though the velocity is not changing magnitude, right? You can see here v1 and v2 are the same length, but there is a change in velocity occurring still, and that changes the direction, right? So you can see in the triangle, the green triangle there, that the two velocities are the same length, but they have a different direction, and the direction between them is that change in velocity. That change in velocity is the centripetal acceleration. So here we have the build-up to the equation for it. So this isn't it yet, we're getting to it, but so because of the two triangles we had on that last slide, with that maroon triangle in the middle of the circle and the green triangle outside the circle, they are both isosceles triangles. Not only are they both isosceles triangles, they are actually similar triangles. And so because they are similar triangles, that means that their sides are proportional to each other. So we can set up this proportion here, where we have the change in velocity, which was that one side by itself is over the velocity, which v1 and v2 are the same, so that is equal to the arc length, which now arc length is the curved part of it, but really when you get down to a small enough sliver of the circle, the arc length and the chord are really the same, and that's mentioned on the previous slide as well. So arc length over the radius are the two same parts of that triangle, that the delta v change in velocity and the velocity were for that other triangle. So that means that we have this proportion occurring. If we solve this proportion for delta v, then we have v over r times delta s. Well, from our previous notes, we know that if we divide everything, both sides, by delta t, on the left side we've got change in velocity over change in time. Well, going back to kinematics, the definition of acceleration is that or average acceleration, is that it's a change in velocity over change in time. So we can change that to average acceleration or just acceleration. And Then on the other side of it, we have this multiplication occurring. But if you recall from last week, or our last video, delta S over delta T was also the linear or tangential speed. So that means we have V over R times V. So that means we really have the velocity squared, and that is the equation we want to write down. So our centripetal acceleration is the linear or tangential speed squared divided by the radius. Now, we can adjust this if we have angular velocity given to us. If I take my angular velocity equation, or my linear velocity equation, that's the linear velocity in terms of the angular velocity, so r omega. If I plug that into v, I get r squared over omega squared, r squared omega squared, sorry. And so then we've got r squared omega squared over r. The r's cancel, or one r cancels in the numerator, canceling the one on the bottom, in the denominator, leaving us with 1r and omega squared, which is the second equation here. So we already wrote down the first equation. You want to write that one down a second time. And they explain all of what I just explained in the paragraph to start here. Again, subbing in v equal r omega. For v, you get r omega squared in parentheses. So that means the r and omega are both squared in the numerator. And so the one r in the denominator is canceled out with one of the two r's in the numerator, leaving us with just one r times omega squared. So what unit is the unit for centripetal acceleration? So looking at these units here, we've got meters per second squared. That's our typical one. Kilometers per second squared, not a typical acceleration unit, but it is one, but not one that is our standard unit. Then the other two, radians and radians per second. Radians is just a unit for angle, and radians per second is our unit for angular velocity. So it has to be meters per second squared. So this next portion is going to bring in this thing called a centrifuge. So we do want to write down what that is, so we have it, so we know what it's talking about. But it is a rotating device used to separate specimens of different density, and you can cut of different densities. You can just cut it off there. And there's all kinds of these centrifuges too. We'll talk about a couple different versions of them in a minute here, but we do have this problem here. So centripetal acceleration versus acceleration due to gravity. So we have a couple of problems we're going to want to solve with this one. So it asks us for two things. One is to find the magnitude of the centripetal acceleration of a car following the curve, radius of 500 meters, speed is 25 meters per second, and we want to find the acceleration that is due to gravity for this fairly gentle curve taken at highway speed. So we have a linear speed here, so that means our AC is going to be equal to v squared over r, v being the 25 meters per second, and our r being 500 meters. So plugging those in, 25 squared over 500. 25 squared is 625 over 500, which is 1.25. And that is meters per second squared. So how does that compare to gravity? So what we want to do is we're going to divide that by gravity. So first off, that's one of our two answers here. 1.25 divided by 9.81. So we want to see how many g's of force they are feeling as they go around this curve, or g's of acceleration, really. So that comes out to be about 0.127, which is not much. It's not even a whole g, right? All right, so let's take a look at their work for it, which should be pretty much the same idea here. And there we go, same work. They got the 1.25 meters per second squared. And you can see in the discussion portion there that they round differently, so they do get a different answer there, but 0.128 Gs, which is noticeable because again, in this situation, it says they're not wearing a seatbelt. Hopefully you are, right? So our next situation, now we have this ultracentrifuge. We're not going to define that. It's pretty obvious what that means. It's a very high-powered centrifuge, so it spins very, very fast. This time, though, we are given the radius is in centimeters, so we need to convert that. And then we also are given the angular velocity, but in revolutions per minute, so we need to convert that to radians per second before we can then use it to calculate the centripetal acceleration. So again, here we have, again, since we have omega, we're going to use the AC is equal to R omega squared formula. And again, R is in centimeters, so we need to convert that. So 7.5 centimeters is 0.075 meters. Then we have the revolutions per minute that is spinning at. So we need to convert that to radians per second. So 7.5 times 10 to the fourth would be 75,000 revolutions per minute. Now, we know that there's, in one revolution, there's 2 pi radians. And then we also know that in 1 minute, there's 60 seconds. So multiplying across and dividing will give us our radians per second. And that is going to be 7,850 radians per second. So we're not done yet. That is our omega. So now we have omega. We've got R ready to go. So AC is going to be 0.075 times 7,850. That's squared 7,850 as well. So we finally get our answer. We're going to go ahead and put this in scientific notation as well. So it's 4.62 times 10 to the third. Oh, sorry, actually. That's sixth meters per second squared. Now this one also wants us to determine the ratio of that due to gravity. So we will take that and divide by 9.81 again. And that comes out to be quite a bit still. 4.71 times 10 to the fifth G's, which is quite a bit. Very, very fast, which again is why it's called an ultracentrifuge. So let's see how they did this. So there's our radians per second again, which is what we got. It's off a little bit. I did round pi to 3.14 when I did my calculation. That's probably where that rounding came from. But not too far off for the rest of our work. They got 4.63 times 10 to the 6. We said 4.62. And then, again, off by a hundredth in the scientific notation forms. And that's not too shabby. So it spins very, very fast. 472,000 times gravity. All right, so here we have this problem where a parent is pushing their child on a swing. The mother is pushing the child on a swing. His velocity is 9 meters per second. At the lowest point of his path, the swing is suspended 2 meters above the child's center of mass. We want to figure out the magnitude of the centripetal acceleration of the child and the magnitude of the force the child exerts on the seat if his mass is 18 kilograms. Then we're going to see about how reasonable the results are. Does the centripetal acceleration make sense? Does the magnitude of the force make sense for what the child's going to be feeling as well? Alright, so let's take a look at this problem here. So our radius is 2 meters, and the velocity is 9 meters per second. We want to figure out the centripetal acceleration at the lowest point, which means r is 2 and v is 9. So for A, we're looking for AC. Since we have v, we're going to use v squared over r. So that's going to be 9 squared over 2 over 81 over 2, which is 40.5 meters per second. That's a very high acceleration for swing, so that's concerning already. For part B, the magnitude of the force the child exerts on the seat. So given the mass, and we know the acceleration, the centripetal acceleration now, but we have to include the fact that gravity is actually acting here as well. So really our force is equal to the kid's mass times both the centripetal acceleration and gravity. So that's going to be 18 times 40.5 plus 9.81. So 18 times 50.31. And that comes out to be a force of 905.58 newtons. Now, part C, is this reasonable? Probably not. Not for an everyday swing. It's a pretty high acceleration rate. It's also quite a bit of force for a child to be exerting on a swing. Whether the swing could handle that and how good of quality the playground is would definitely come into play, but probably not, can I say. So this is just reiterating that the next thing we're going to take a look at is centripetal force. Remember, centripetal again means things that point towards the center or center facing. So centripetal force is the force that goes along with centripetal acceleration.